Hello everyone, I'm Sai from Roman. I'm going to bring a presentation for the course Theory of Computation. The topic I've selected for my tech talk presentation is material programming. Let's begin. Let's get on to the basic introduction of material programming. Material programming basically involves creating computational models and languages to study and solve abstract problems. It allows for exploration of complex concepts and the development of innovative solutions. This approach is highly interdisciplinary, drawing from fields such as computer science, mathematics, and physics. Let's see more about it. So basically, in the near future, every other smart material will have a computational power embedded in the form of graphene transistors or nanotubes. Uh, this will ultimately improve the computational composites. So the basic qualities include such as durability, flexibility, texture, weight, and color, but additionally, being capability of sensing, actuating, and computing. So basically, material programming would complement traditional crafting of physical form with the crafting of temporal form, and together by they would make up the future practice of interaction design. Material programming practice would be a programming practice using physical tools uh, with tools in hand working directly with materials. The designer would be able to achieve an embodied sense of its interactive and expressive properties. Such tools would each have a specific function design from the designer's point of view, rather than a programming logistics point of view. By also limiting the scope of each tool's action or space, it will be possible to create rather sophisticated tools in terms of what the designer can do with them. So, by envisioning a material programming practice, central to the practice of interaction design is crafting the couplings and relationships between user actions and artifact functions. So, understanding abstract problems. In order to be able to program materially, we need to understand the abstract problem, then solve them. Abstract problems are often complex and challenging to solve using traditional methods. Material programming provides a framework for breaking down these problems into manageable components. By representing abstract components in a computational model, researchers can gain new insights and perspectives. So let's define abstract thinking. Abstract thinking is a type of higher order reasoning about symbolic and hypothetical ideas and principles. It involves conceptualizing problems, extrapolating outcomes, and arriving at logical and rational conclusions on topics that are often intangible. For example, working around problems, an engineer saw that the bridges company was trying to build across a valley was going to be expensive. So he brainstormed a new idea that he would build tunnels himself. So this is what abstract thinking is. So sketching a multi-programming practice includes to give a better sense of what we mean by tools of material programming. We here present some sketches of physical tools for programming computational composites. In order to convey functionality of these tool sketches, we assume the existence of very particular computation composite, a shape-changing material that can respond to airflow. We imagine this computational composite to be used in interior design and architecture. For instance, in interactive package or in furniture, through speculating and enacting the practice of shaping the behavior of this composite to discuss qualities of what material programming for interaction designers would look like. Here are some advantages of material programming. Material programming enables researchers to simulate and explore complex systems that may be difficult to study in the physical world. It allows for rapid prototyping and testing hypothesis in controlled environment. By creating computational models, researchers can gain a deeper understanding of abstract concepts and phenomena. Building on related programming practices. In most cases, the default mode of programming computers is textual. There are, however, alternatives to textual programming languages that are relevant to discuss in relation to material programming. Visual programming or tangible programming and programming by example, for instance, all support explorative design techniques practices by minimizing the distance between programming and execution. We will here discuss the relation between qualities of these programming practices and material programming. Creating computational models. Computational models in material programming are built by using mathematical and programming languages. These models simulate the behavior of abstract systems and allow researchers to test various scenarios. By adjusting parameters and inputs, researchers can explore the dynamics of complex systems and analyze the properties. Here are a few programming models, such as data parallel model and task parallel model. In data parallel model, we have single instruction, multiple data, single program, multiple data, multiple programs, multiple data. So this includes an architecture. It's FIMD architecture and MIMD architecture. So let's discuss some things about visual programming. Visual programming works by replacing textual code with visual notations, such as 2D representations, and tools as meant to construct software. This visual programming utilizes people's ability to easily recognize and work with visual patterns, and thereby minimizes the need for learning. Visual programming is good in aiding rapid development, and particularly in the early stages of design. This is partly due to low threshold of changing the logical structure of program, which makes it easy to experience multiple design alternatives in explorative manner. Designing languages for material programming. Languages for material programming are designed to be expressive, and flexible, accommodating a wide range of abstract problems. These languages often incorporate features from multiple design disciplines such as logic, algebra, and statistics. By designing special languages, researchers can tailor their approach to specific problem domains and optimize the computational efficiency. Material programming would also utilize this lateral quality since programming and execution happens in the same material realm. A textual or graphical overview of data structure and algorithms would, however, not be an integrated part of this practice, although it could be made available somewhere else. Here is a case study, neural networks. Neural networks are popular application of material programming used for modeling and simulating the behavior of the brain. By creating computational models of neural networks, researchers can study learning algorithms and cognitive process. Material programming allows for exploration of complex neural networks and their applications in artificial intelligence. Now let's just brief about why a material programming practice. Why do we need material programming practice? In this feature, we presented the notion of material programming as a future practice or designing computational competency. Such practice would be a way for designers to explore, experience the dynamics of computational materials they are working with. This in turn will support the designers kinesthetic creative practice, and we will believe they will become capable of composing more sophisticated and complex temporal forms in the designs. We propose this practice knowing that the current technology and materials are not entirely ready to support it, but we are convinced that they could be not a too distant future. The future material programming practice will not look like a one proposed above. The contribution here is therefore just arguing for the qualities that practice would embody in this four role. There are four basic things. Firstly, a material programming practice should not rely on direct representation of programming actions performed on any performed on material beyond material itself. Here is another case study. It's an application of material programming, quantum computing. Quantum computing is another area where material programming plays a crucial role, enabling the researchers to simulate quantum systems. By developing computational models of quantum phenomena, researchers can explore the potential of quantum algorithms and technologies. Material programming allows for design and optimization of quantum circuits and algorithms for various applications. Challenges in material programming. One of the challenges in material programming is the complexity of abstract problems and their computational representation. Developing an accurate and efficient computational models requires a deep understanding of the underlying principles and behavior of the system. Researchers must carefully validate their models and ensure that they capture the essential features of the abstract problem. Future directions in material programming. The field of material programming is rapidly evolving with new techniques and approaches being developed. Future researchers may focus on creating more powerful and expressive languages for modeling abstract systems. Advancements in hardware and software technologies will continue to drive innovations in material programming, enabling researchers to tackle even more complex problems. Conclusion. Material program thus offers a powerful framework for studying and solving abstract problems using computational models. By creating specialized languages and models, researchers can gain new insights into complex systems and phenomena. The interdisciplinary nature of material programming makes it a versatile tool for exploring a wide range of scientific and technological challenges. We have come to the end of the presentation. Hope you like the presentation on material programming. Thank you for your time.